Now here in this question it is asked that let Np and Ne be the number of holes and conduction electrons in an extrinsic semiconductor. So Np is the number of holes and Ne is the number of conduction electrons or free electrons. And here we are going to analyze an extrinsic semiconductor. So the options here are whether Np is greater than Ne, that is number of holes is greater than number of conduction electrons, whether Np is equal to Ne, that is number of holes is equal to number of conduction electrons, whether Np is less than Ne, that is whether number of holes is less than number of conduction electrons, and whether Np is not equal to Ne, that is whether number of holes is not equal to number of conduction electrons. This is what we are going to analyze in an extrinsic semiconductor. Now to do the analyzing of this, we will start with the first basic definition of what is an extrinsic semiconductor and then what are the types of extrinsic semiconductor. So to start with, what is an extrinsic semiconductor? An extrinsic semiconductor are those semiconductors that come into existence when a measured and a small amount of chemical impurity is added to the intrinsic semiconductor, that is pure semiconductor. It is also known as doped semiconductor or impurity semiconductor. The doping of the semiconductor increases its conductivity. That is, when we have intrinsic semiconductor, its conductivity is less. So to increase the conductivity of intrinsic semiconductor, we add impurity to the intrinsic semiconductor. That process is called as doping, and we do this to increase its conductivity. So extrinsic semiconductors are those where conductivity is high. The process of deliberately adding a desirable impurity is known as doping, and the impurity atoms are called as dopants. So the impurity what we add to the intrinsic semiconductor to become extrinsic semiconductor are called as dopants. Now, while doping tetravalent atoms such as silicon or germanium, now we know that silicon and germanium are the two purest form of semiconductors and they are tetravalent in nature, that is they have 4 valence electrons each. Okay, so while adding impurity to these tetravalent atoms such as silicon or germanium, we have two types of dopants. The first type of dopant is called as pentavalent atoms. So these are atoms with valence electrons 5. So pentavalent atoms are those dopants which have valence electrons 5. There are 5 valence electrons in these elements, and examples of pentavalent atoms are arsenic, phosphorus, antimony, etc. We also have one more dopant called as trivalent atoms. So these are atoms with 3 valence electrons, and example of this are indium, aluminium, boron, etc. Now, when a pure semiconductor like silicon or germanium are doped with pentavalent elements, a n-type semiconductor is created. And when a pure semiconductor like silicon or germanium are doped with trivalent elements, a p-type semiconductor is created. Now with this concept, we will enter the logic of this question. Now extrinsic semiconductors, we know they are of two types, n-type semiconductors and p-type semiconductors. Now let's see first n-type semiconductor. Now here we will be having a pure form of semiconductor called silicon, and there are many silicon atoms in this lattice shown above. So to these set of silicon atoms, we will just add a single phosphorus atom. So here you can see this is the phosphorus atom, and it is a pentavalent element. It is a type of pentavalent dopant because it has 5 valence electrons. So here you can see the electrons in the outermost orbit for this element called phosphorus. We have 5 valence electrons. This is 1, this is 2, this is 3, this is 4, and this is 5. Now when we add this phosphorus atom, a small amount of phosphorus atoms to a set of silicon atoms, so we can see this here as an example. One phosphorus atom is added to these many silicon atoms. So here you can see the 4 valence electrons of phosphorus will make 4 covalent bonds. So here you can see The valence electrons of this silicon is making covalent bond with the valence electron of phosphorus. So here you can see the valence electron of this silicon is making a covalent bond with phosphorus. Here you can see valence electron of this phosphorus making covalent bond with the valence electron of this silicon atom. And here also you can see valence electron of silicon atom is making covalent bond with valence electron of phosphorus. So 4 of the 5 valence electrons of phosphorus are making their respective covalent bonds, and 1 electron will become free, and this free electron will be a conducting charge carrier. And therefore, if you add a small amount of phosphorus, that is a few phosphorus atoms to a set of silicon atoms, then we will get many of such free electrons. And therefore, because the number of free electrons are more in this arrangement, this type of semiconductor where a pentavalent atom is added to a pure semiconductor is called as N type of semiconductor. So here you can see this is the concept of N type of semiconductor. So in N type of semiconductor, the number of electrons are more. The number of conducting electrons, that is free electrons, are more. So it is called as N type semiconductor. Similarly, if you see the concept of forming a p-type semiconductor, so here we will take a dopant which is trivalent in nature. So here you can see we will take a boron atom. So boron atom will have 3 valence electrons. So here you can see in its outermost orbit we have 3 electrons. This is 1, this is 2, and this is 3. When boron atoms are added to pure semiconductor like silicon, so here you can see one example of a boron atom added to silicon atoms. So what will happen? Here you have boron atom. Now boron atom is having 3 valence electrons. So all these 3 valence electrons will make covalent bonds with the respective adjacent silicon atom valence electrons. So here you can see this is one covalent bond between the valence electron of silicon and valence electron of boron. Here is one covalent between the valence electron of boron and valence electron of silicon. Here is one covalent bond between the valence electron of silicon and valence electron of boron. But here the 4th valence electron of silicon, because silicon is a tetravalent in nature, will not have any electron from the boron side to make a covalent bond. So here in this place one electron is missing, one electron is short. And this place of electron where there is no electron or electron is short, this is assumed as a hole. This is assumed as a hole. So here we are getting one hole because we are adding trivalent impurity to the tetravalent silicon pure atoms. So if you add such small amount of boron atoms to silicon atoms, we will get many such holes. And because we get many such holes, and holes are considered as positive charge particles, and we have many of these charge carriers which are holes, therefore this type of semiconductor is called as p-type semiconductor. So in p-type semiconductor, the charge carriers holes will be large in number as compared to free electrons. Then to conclude with, we can say that extrinsic semiconductors are formed by doping either an N-type material or a P-type material with a pure semiconductor. Thus, it may have more number of holes if the doping material is P-type. So as we have seen, if the doping is of P-type, we have large number of holes. Or it can have more number of electrons, that is free electrons, if the doping is of N-type. So if the doping is of P-type, we have large number of holes. And if the doping is of N-type, we have large number of electrons. So here we can conclude that if the doping material is of P-type, then we will get large number of holes. So we'll get large number of holes in an extrinsic semiconductor, and electrons will be less. And here if you see, if the doping material is N-type in nature, then we'll get large number of electrons in that particular extrinsic semiconductor. Therefore, in an extrinsic semiconductor, either there are large number of holes if it is p-type semiconductor, or there are large number of electrons if it is n-type semiconductor. That means either holes will be more or free electrons will be more. Both will not be same. So the number of holes will not be equal to number of electrons as a complete concept of extrinsic semiconductor. If you see whether it is a n-type semiconductor or p-type semiconductor. If it is n-type semiconductor, there are more number of free electrons. If it is p-type semiconductor, there are more number of holes. Okay, so either of this will be more and the other one will be less. That means both number of holes and number of free electrons are not equal. One of them will be more, taking into a consideration whether it is n-type or p-type, but both cannot be same. So it is not equal to each other, because we cannot say that number of holes is more than a number of free electrons. If it is number of holes more than number of free electrons, then it will be p-type semiconductor. If number of electrons are more than number of holes, then it is n-type semiconductor. But if we are speaking for extrinsic semiconductor, then we cannot speak specifically for p-type or n-type. We have to speak for complete extrinsic semiconductor. So for complete extrinsic semiconductor, the number of holes will not be equal to number of electrons. That is the concept. And for that, the last option, that is NP not equal to NE, will be the right answer. So in an extrinsic semiconductor, NP will not be equal to NE. We are not speaking here specifically for p-type or n-type. If you speak for p-type, then NP will be more than NE. If you speak for n-type, NP will be less than NE. But we are not speaking for p-type or n-type. We are speaking here for extrinsic semiconductor. And for extrinsic semiconductor, the number of holes will not be equal to number of electrons. Either the holes will be more as in p-type, or the electrons will be more as in n-type. But for extrinsic semiconductor, both will not be equal to each other. So option D will be the right answer here.